So without further ado, what I'm going to be talking about is my academic research and has nothing to do with machine learning or data science, as you can tell from the title. Matroids and high energy physics. Before I left academia, I mean, my academic research is still in kind of combinatorics and high energy physics, and that's what we're going to be talking about today. So this is a talk in 3 acts. So Act 1 is all about matroids and positroids. And I'm going to go through and define all of my terms. I was told to kind of give this at a undergraduate level, so hopefully everybody in the audience has had some linear algebra. That should be all you need. If not, raise your hand to tell me to slow down, and I absolutely will. So I'm going to start with a matrix. Yeah, right now I'm going to be starting with a 2x5 matrix. I'm going to be having this as a running example throughout the entire talk. So for this matrix, I'm going to be talking about K by N matrices where K is equal to the number of rows. And so this is going to be my rows, and this is going to be my columns. And just N is always going to be bigger than K. Like I just need to set a convention, and I guess it's going to be bigger than equal to. I'm not ruling out square matrices, but they're always going to be, short, wide matrices is the type of matrix I'm going to be looking at. You can always take the transpose and kind of do things differently if you have a different type of matrix. It's not a huge deal. All of my entries are going to be in some sort of a ring. In this case, they can be in Z, they can be in R, they can be in C, they can be whatever. In this case, by and large, I'm going to be looking at entries in R, but that is going to change a little bit. And the other thing that is not necessarily always true of all sorts of all matrices, but I am going to require here that's special, is that my matrices are full rank. None of this generalizes nicely if I have to worry about what the actual rank of my matrix is. If I write a matrix, I want it to be in full rank. If it's not in full rank, row reduce and get rid of one of your rows. That's kind of the starting hypothesis for all of this. Okay, so given all of that, I am going to talk about what a Grassmannian is. I know Act 1 is matroids and positroids. The Grassmannian is a surprise character. We will see why he's introduced. So a Grassmannian, so in this case, again, I'm still in this case where I'm still looking at this matrix. And what I want to think about it, of a Grassmannian as, is it's a set of K vectors in Rn. Remember, K is my rows, N is my columns. So I have some n-dimensional space. In this case, I have a 5-dimensional space. And I have 2 vectors, 1, 2. So I'm just taking a look at all of the spaces that are spanned by 2 vectors in Rn. So in this case, planes in Rn. Why do I know that these are always going to be plane? Well, remember, planes, I demanded that all of my matrices be full rank. So the 2 vectors are going to always be 2 independent vectors. So, and 2 vectors always define a plane. So I'm at 2 vectors in Rn. So I'm looking at 2 planes in Rn5. And then the question that I have is, okay, so this matrix here will give me 2 vectors, but it's not unique, right? Like there's lots of other matrices, there's lots of other vectors that can define the same plane. So for instance, I can go through and do some matrix multiplication, and all I need to do here is I need to make sure that the determinant of this matrix is not 0. Just take any 2x2 matrix with a non-zero determinant and do a left multiplication, and I'll get another matrix. And this will define the same plane, right? So that's another point. That's another matrix that's represented by the same 2 plane in Rn. So at this point, so now I can, right, so all I did is I went from this picture here, I did a matrix multiplication, and I went to that picture there, right? I did some sort of linear transformation on the 2 vectors that were defining my plane. I get a different set of 2 vectors, but they're still lying in the same plane, right? So that's all that a Grassmannian is. I'm thinking about the planes. I don't really care about what the matrix is. What I really care about is somehow a equivalent set of matrices. Like there are multiple different matrices that talk about the same 2 plane in Rn. So if I go through more explicitly, my Grassmannian, I can talk about it as being represented, not defined by, but being represented by a matrix. But it's going to be defined by these objects that I'm going to need later, and which was the entire point of talking about the Grassmannians at all. They're going to be defined by Plücker coordinates. So what are my Plücker coordinates? Okay, so in this case, what they really are is if I go through and take my five columns and I give them names A through E, I'm just going to be taking a look at all possible 2 by 2 minors. So AB, that minor is 13. AC, that minor is 0. And you can go through and check my arithmetic and make sure I'm not trying to hoodwink you. AD is 3, etc., etc., etc. Okay, so all I'm doing is I'm taking a look, if I want to compute, let's say BE. So I take this column, and I do AD minus CB. And I get -3, hopefully, if I've done my arithmetic correctly. So Plücker coordinates, they are just the K by K, they're all possible K by K minors written down in some way. Now, there's a trick. This is unique to a given matrix. Not unique, but this set of coordinates corresponds to this matrix. But earlier, we said that this matrix and this matrix both represent the same point in the Grassmannians, the same 2-plane in Rn. So that's a problem, right? Because when I go through and do the minors of this matrix, I end up with that factor. And when I end up do the minors of this matrix, I end up with that factor. Now, if we stop and think about the matrix that I did the multiplication by, I think it was 1, 1, 2, 4 was how I was the matrix I multiplied. This has determinant 2. So there's a scaling factor of 2. So all I've done is I've scaled, I've just, if I think about the determinant as taking a plane and just kind of stretching it, and the determinant tells me exactly how much the plane is being stretched. So that's all I'm doing is I'm just stretching all of the 2 by 2 minors by 2. And so my Plücker coordinates, really what I want to think about them as is I want to think about them as these types of vectors, but up to a scaling. So 1, 1, 1 is the same thing as 2, 2, 2 is the same thing as -1, -1, -1 is the same thing as, etc. Okay, so what I've done so far is this first step. I've gone from matrices, which are K vectors I just have a bunch of vectors and I just list them out, and each different vector is each different collection of vectors corresponds to a different matrix, to a Grassmannian, which now I don't care about what the individual vectors are. What I care about is the planes that they span. So a set of vectors that span, two sets of vectors that span the same plane, same point in the Grassmannian. Now I'm going to generalize a step further to get to the matroid, which is the actual place that the object that I want to study. Okay, and I'm going to lie a little bit because everything here is a representable matroid. I'm going to drop the word representable. There are objects that are non-representable matroids. I'm not going to worry about them because I don't care about them for this talk. So the matroid structure is all that it cares about is which of my Plücker coordinates aren't 0. It just cares about, it says that, I have a K by N matrix. The only thing I care about is which of my Plücker coordinates are not 0. It doesn't care. So now so in this case, it says that, everything other than AC is non-zero. Well, that's my matroid structure. It's all of those other terms. So all it's saying is that A and B are independent. A and C are not independent, so I don't care about that pair. A and D are independent. A and E are independent, etc., etc., etc. It just cares about which Plücker coordinates aren't 0. So in this case, I give you a matrix, and you say, what's the matroid to it? You say, well, everything other than AC is independent. That's my matrix structure. So I've stopped caring about planes. I've started caring about just the independent structure. Okay, so that's a matroid. There's an awful lot of really pretty combinatorics that go on with matroids that if you want to ask me about later, I am more than happy to talk your ear off. I do not have time to go through it in an hour. So, actually, before I go on to this page, I just want to kind of, maybe I'll pause here and say, note that since I'm only caring about everything that's non-zero, I could go through, I no longer, this is a generalization of the Grassmannian in the sense that I don't have to only be able to multiply these guys by 2 or -1 or 4.5 or pi. I can really just arbitrarily, let me just choose another color and just do it like this. I could also just change this to 5 and this to 2 and this to -1 and this to 42 and this to 1004 and this to e because y should be just be using integers and this to 5 halves and this to 1 and this to 1 because I'm running out of creativity. Right? That's still the same matrix. Because the only thing that's non-zero is still AC. Right. So now instead of insisting, like instead of with the Grassmannians, I've said, okay, everything that's scales with this initial vector that I gave you is going to correspond to the same Grassmannian, point to the Grassmannian. Here I'm saying anything that has the same independent structure, anything that has the same non-zero Plucker coordinates corresponds to the same matroid. So this is a vastly larger and in some ways messier object to be dealing with. Okay, so it really just is which Plucker coordinates are not zero. That's the only thing I care about. I don't care about the values of the Plucker coordinates, except in that I care about that they're not zero. Okay.
Sorry for interrupting.
Yeah, please interrupt.
So for the Grassmannian, we do require those Plucker coordinates are in ratio with each other. That
Yes.
Modifying them. But the matroids do not require, the only cares which ones are not zero.
Exactly. Oh. Yes, that's the key difference between them. That's why I'm saying that the matroid is a generalization of the Grassmannian. Okay.
All right. Okay. Thank you.
Mm-hmm. Okay, so those are big and messy, and there's a large body of work that tries to kind of put order to matroids. But I'm going to talk about a smaller subset of matroids, which are called positroids, which have much nicer geometric properties. So I'm going to talk about a positroid. And now we've kind of introduced all of our characters for it. So all I require for a matroid to be a positroid is that all of the coordinates are greater than or equal to 0. So our favorite hero here we see is actually not a positroid because we have these three coordinates are non-zero, are positive. And in fact, it's even more than that. It turns out, if you're very careful, that if you take, well, actually, let me rephrase this, because I think, give me 1 second. Yes, I'm going to rephrase this, and I'm going to change this because I think this is a little bit misleading. Okay, so what Yifei just asked a little bit ago was saying that, can we have this structure and have all the Plucker coordinates be positive? And the answer is, what Yifei just asked is, can we have, the only thing the matrix cares about is that these entries are not zero. It doesn't necessarily care about that the entries are kind of in some sort of a scale relation with each other. And the thing that I was doing on the previous page was arbitrarily putting down values. I was being a little bit tongue-in-cheek there, because you can't actually just arbitrarily put down values for matroids because there are relationships, right? Like if I have A and C is a relationship between, let's not do A and C. Let's do A and B is the relationship between those two guys, and B and D is the relationship between those two guys, then that automatically gives me a whole lot of information about my relationship between A and D. It's not deterministic, but there is a relationship there. So it's not completely arbitrary. So I want to be very careful here when I talk about this. When I take a look at this matroid, or the matroid that this matrix represents, I see that, oh, look, there's some negative numbers here. And you might want to think, oh, wait, this isn't a positroid. But it turns out, and I wish I'd done this calculation ahead of time, and because I just was not thinking carefully enough. It turns out that in this case, there is a different matrix with the same independent structure, such that all coordinates are greater than or equal to 0. So you can go and find that. I might just leave that as an exercise to the reader. I know that's obnoxious, but it shouldn't be that hard to find in this case. The only restriction really here is that the first column and the third column are scalar multiples of each other. And you can just start putting in very basic numbers and it should fall out at the end. That this independent structure does have a matrix with all non-negative minors. And you just have to be able to find it. So a Plucker coordinate doesn't mean, so this is a positroid doesn't mean that every matrix that represents it has positive Plucker coordinates. It just means that there's some matrix where all the Plucker coordinates are positive. Okay, so here's another example. This one does have all Plucker coordinates that are positive in this representation, just to kind of give you a not negative example. And the other thing that I want to point out, and this one is simpler, it's just in 3 coordinates. The other thing that I point out, because I'm talking about determinants being greater than or equal to 0, all of my entries must be real. I can't do this in the complexes because there's no concept of greater than 0 when I'm talking about 1 plus 1i. So once I've talked, matroids can be in anything. Positroids have to be based in the reals. Okay, so that's what a matroid is and what a positroid is. Oh, nope, I lied. I have a little bit more on them. The nice thing about positroids is that they have a really nice geometry. So, and this is why I like them. I was talking to Yife earlier about how I am very much a geometric-minded person. So the reason that I like positroids is they have a nice geometry. And the easiest place to see this is if I'm taking a look at n equals 3, k equals 2. So what I can do, and what happens here is that they form something that's called a CW complex. If you don't know what a CW complex is, don't worry about it. But what you end up with is you end up with a shape. So if I have all 3 of my minors are not 0, or actually are positive, then that gives you this triangle. It gives you a 2-dimensional shape. And it turns out that there are 3 boundaries to this 2-dimensional shape. And that's why I'm drawing it as a triangle. One of them is when both AB and AC is greater than 0. Another one when BC and AC are greater than 0. And the other one is when the last pair is greater than 0. So those are your 3 options for your boundaries. And each of these lines, and the reason I'm drawing them as lines is because they each have 2 boundaries that are 1-dimensional, and that's the intersection. So AB and AC and BC and AC have one intersection that's AC is greater than or equal to 0. BC, AC, BC, AB have one intersection that's when BC is greater than or equal to 0, etc. So you really can find this very nice geometric structure. You can talk about a space, you can talk about what the boundary of the space is, you can talk about the dimension of the space. You can start taking a subspace that I'm going to call positive Grassmannians, which you don't have to worry about too much. But they're Grassmannians with positive Plucker coordinates, and you can start decomposing that into according to which positroids belong to. There's a nice partitioning. There's just all sorts of really nice geometry going on there. We'll come back to that geometry in a bit. Act 2, Feynman diagrams. Okay, so we're leaving geometry behind completely, and we're going to be talking about high energy physics. And the fundamental question that we're trying to study here, we're trying to gain some traction on, is what happens when two photons collide. I could change this to electrons, quarks, whatever, right? I want to take it, I want to talk about when, and I could change this to some number of particles. What happens when a bunch of particles collide? So when we talk about CERN, which is now Large Hadron Collider, these are the types of experiments that are going on there in real life. And the mathematicians, the mathematical physicists are trying to run along aside behind the theoretical, the experimental physicists, and try and really put some order to the findings that are coming out of these large labs. And so that's where Feynman diagrams come from. And what Feynman diagrams are, so if you've had linear algebra, I'm assuming most of you have seen a little bit of Taylor series already. And what I'm looking at is I'm going to say, okay, I have this function. I know what happens when two particles collide because I can measure it in CERN, in the outputs of CERN. But I don't know how to calculate what that number is. I don't know how to approximate it as a function. So I'm going to go through and approximate it with all sorts of with a what if of different possible interactions happening, and I'm going to assign a scattering amplitude, which is roughly, very roughly, can be thought of as a probability of each of these various things happening. So the most likely thing that happens is they collide and nothing happens, right? That's possible. Another thing that happens is that it spouts out an electron and an anti-electron. I said proton, I meant positron. Shame on me. And an electron anti-electron pair. I could have a more complicated thing. Here I have, I'm going to zoom in to kind of look at this more. I have the photon going this way. I have a electron and a positron going that way. And all of a sudden it just sporadically decays for no reason other than its own whim into a photon and into its antiparticle, which then collide and form an electron, a photon again. So, and that's the equivalent of having two photons collide. So you can get more increasingly complicated things coming out of the scattering. And Feynman diagrams are a nice way of being able to picture what are all of the possibilities that can happen, assigning a scattering amplitude or a probability of let me just say scattering amplitude to each one. And then we add them all up, and after you do a few more calculations, after you're adding them up, you get the initial output of what you're seeing in the lab. So, right, and so what's going on behind each of these is that each of these diagrams, each of these, I've dropped the more complicated ones, but each of these little diagrams correspond to an integral. It's called a Feynman integral. And that gives you the probability. I'm going to not worry about the integral for now, and I'm really going to just stay focused on the diagrammatics of this. Okay, one thing that is interesting and important for this paper is that very weird things happen with parallel lines. So in the previous picture, I showed you, two things coming at each other, and I was asking a question of what happens in there. So I had one photon coming from here and one photon coming from there. They were coming from opposite ends, they were colliding, and we were studying what was going on. If they don't come from opposite ends, if they're basically traveling together and they collide, that's one place where the physics gets very strange. So if I think about, in this picture, I can still talk about it. It's a different version of them coming from the opposite angles. You can think of it as just kind of, oh, I'm just turning the angle knob, And okay, so that's just a parameter, and maybe as that parameter changes, I get a different value, and whatever, that's fine. But when they're really coming in at the same angle, well, all of a sudden I've taken my limit to 0. And all sorts of weird things happen when parameters are allowed to go to 0 that are normally not 0. And the picture that is drawn here is just, it's called a tadpole diagram. All of a sudden, instead of it looking like there's 2 photons interacting, there's only 1 photon interacting, and then therefore there's only one. Is this an electron? Is this an electron? Is it a positron? It's going back into itself. What's going on? So this entire phenomenon of when things are parallel is called an infrared divergence. And when I said we have these integrals and then we add them up and then we have to do a few more things, one of those things is dealing with these infrared divergences. So I'm not going to go into a whole lot of detail of what they are. I'm just going to point out that infrared divergences are a thing that physicists worry about and that I'm going to be worrying about in my talk as well. Okay, so these guys are the pride and joy of my life. They are, well, don't tell my son that. They are called Wilson loop diagrams. They are a generalization. They are of Feynman diagrams. I'm going to put in quotes for quarks. It's a simplification of quantum chromodynamics, which is the theory that studies how quarks behave. The actual theory that these arise from is SYM n equals 4, supersymmetric Yang-Mills theory at n equals 4. And this picture here shows you that there's 8 interacting particles. That's what the numbers 1 through 8 around the outside are. And there's 3 helicity violating propagators. I think I wrote this, but I never said this. Nope, I never wrote this either. These lines in here, maybe I'll just put this in blue. These lines in here, the internal particles, these are called propagators. So this diagram up top has 2 propagators. This one here has 1, 2, 3, 4, 5 propagators. If that makes sense. They're the internal lines that are not actually what's coming from the 2 particles that are interaction. They're everything else that's happening internally in the collision. This one here has 1 propagator because there were the 1 photon that just kind of has a propagator that's never detected elsewhere, just kind of appears and disappears. So when I'm talking about 3 helicity violating propagators, I'm talking about 3 special types of propagators. Don't worry about what helicity violating means. Just know that they're a special type of propagator, and they are indicated by these guys, the little wavy lines inside of the diagram. So I have 8 particles interacting. And on the inside, there are 3 special propagators that I'm worrying about. I'm not worrying about the other propagators. That's what this diagram is telling me. So it's a type of Feynman diagram. And the hard and fast physical rule that I have is that my propagators cannot cross. This is not a mathematically defined fact. This is a physically defined fact. This is when I think about physics, I think about, things that are handed down to me from above. And when I think about mathematics, I think about things that, I and my colleagues can create by pure thought. This comes down from above. I can't do anything about it. That's just the way the universe is. But it turns out that fact actually has some very nice mathematical properties that we'll talk about in a bit. So that takes me to Act 3. When the physics knows the geometry. So the physics here was the Feynman diagrams that we were talking about in particle interactions. And the geometry is if you go back to the positroids, and we talked about each positroid corresponding to this geometric space. And yeah, so what I'm going to point out is that the physics of QCD of SYM n equals 4 somehow is fundamentally aware of the geometry of the positroids in a way that is deeply mysterious to me and very, very exciting. I didn't know my quarks were so smart. So again, we're going back to the situation that we had in the previous slide. of 8 particles and 3 helicity violating propagators. And I'm going to write it down as a matrix. That's going to actually correspond to a positroid, or at least a matroid for now. What I have is I have 8 rows and 8 columns and 3 rows. And what I'm going to do is instead, and before I said that they always have to be in a field, here my entries are in R x1 to x, let's say 12. So it's the field of variable, they're variable valued entries over a field.
So the 12 is arbitrary, or does
The
it,
12
is there a
is
reason
3 times 4. Each row happens to have four entries in it.
okay.
Okay. So the way that I fill out this, I hope my dog is going crazy downstairs because the postman's here. I hope it's not bothering you guys too much. I do apologize. So the way that I write down what each of these matrices are is I will take, let's take this one here and just change some colors. And let's talk about that one as this guy here, and let's make it the same color. So why does that row correspond to that propagator? Well, this propagator, the red propagator, has one end on the edge that's defined by 2 and 3. And you will see that in the second column and in the third column, there's a variable, there's an entry there, that's a non-zero entry there. And the other one is supported on the edge between 1 and 8. And you'll see that on the first column and the 8th column, there's some entries. Now, similarly, I can take this one and I'm going to just use a different color. And that one is, make sure I get this one right, it's going to be this one here. Right? Again, supported on 2 and 3, and therefore there's X's there. And it's supported on 6 and 7, and therefore there's X's there. And the white one, again, in the same way, it's supported on 4 and 5, and supported on 6 and 7. That's where the X's are. I want to be very clear here. When I was writing the matrix, I got lazy and I didn't label them 1 through 12, but I really do want them to be independent variables. They're not the same variable in multiple places. They're absolutely independent variables in multiple places. Okay, so I have a particle interaction. I have a matroid, or I have a matrix. I want to point out this isn't just some arbitrary matrix that I'm making up. This is a matrix that appears fundamentally in the Feynman integral that's associated to this diagram. So this matrix is almost also given to me from above. It is given to me from physics. I'm trying to make sense of it. Okay, so now why do I say that the matrix, that the physics knows the geometry? Well, one theorem, maybe I should just actually label this as a theorem, is that if I have non-crossing propagators, remember that was one of the rules that was given to me from above. If I have non-crossing propagators, then the associated matrix is a positroid. As soon as I have crossing propagate, well, not as soon as, the if and only if is in some other direction. And that has a little bit more nuance to it, rather. But as long as I don't have crossing propagators, I have positivity. And as long as if I have crossing propagators that fail to meet some density condition, which is just a complication that I don't want to get into, then I'm going to fail to have positivity. So somehow this rule that physics says that I can't have crossing propagators is telling me that now, oh, look, I want to be in this positive geometric space. I want to be a positroid. So that's fun. Some other things that I know. This theorem here is really a consequence of Hall's matching theorem, if people know that. Hall's matching theorem it's a fairly famous theorem. I'm not a historian. I don't know when it's from. It's on graphs and being able to pair up bipartite graphs. old, used in optimization and all sorts of graph theoretical problems as well. But it a correlate, when it follows from Hall's matching theorem and the structure of these matroids, that if every minimal that my matrix here has a minimal number of varied entries, if every set of R rows has at least R plus 3 columns. So in this case, I see that this matrix here does not have a minimum number of variables, because here's a set of 2 rows, but it only has 4 columns in it. That's less than R plus 3. So this is not minimum. And in this case, you can actually just see it. I can take a look at these 2 rows, and I can do some row reduction, and I can get rid of that and call that a 0. And everything else is still going to have something that's independent and non-zero in it. I'm not going to have added more math somewhere else. So, well, that's interesting. Why am I bringing this up? And the reason that I'm bringing this up is that, again, coming down from above is this observation, a conjecture, that I can't have parallel propagators. So this picture here is exactly those 2 rows that I've been talking about. It corresponds exactly to those 2 propagators, which are parallel. But what do I mean by parallel? They start and end on the same edge in my diagram. Physics conjectures, they can't prove that this should not be allowed. And Hall's matching theorem tells me that if I have this set of rules to go from my diagram to my matroid, to my variable varied matrices, well, yeah, of course it's not allowed, because all of a sudden this isn't minimum. I shouldn't be having that entry because I can row reduce it away. All sorts of weird things are going on. So again, my physics is somehow aware of this underlying geometry, which is fun. Okay, and then I'm getting near the end, and so I know people have to go, and I will be ending early. So one of the issues that I talked about was this infrared divergence from earlier. If you remember, I had 2 particles that were interacting, and that was fine, and they can get arbitrarily close, and that's still fine. But then once they become like right on top of each other and they collide, you've set that angle parameter to 0, all of a sudden things get really weird. And what it turns out is I can study this, what's going on at this, by taking a look, by studying the prime factors of the products of my Plückel coordinates. So I have this matrix. It's 3 by 3, so calculating the Plückel coordinates is a little bit more complicated than before. But if I go through and do it, I will find that my prime factors are always going to be either 1 by 1 or 2 by 2. So, and they will correspond to, for instance, bringing these propagators together, the infrared divergence. So if I take this propagator here, and instead of drawing it like that, I draw it not to be supported on 1 and 8, but I draw it supported so that it's supported only on 1. Well, that corresponds to setting that to 0, that variable to 0. Because it's no longer supported on 8. It's just supported on 1. So I shouldn't have a variable in 8. So if I do that, and it turns out this is a prime factor when I take all the Plückel coordinates and I multiply them together, this is one of my prime factors of that product. Similarly, if I take if I take a look at this one, what do I mean by this one? I'm going to take this propagator, and instead of them meeting at 2 separate points, they meet at the exact same point on the edge. If I do that, that actually ends up corresponding to setting this 2 by 2 minor to 0. And it turns out that 2 by 2 minor is exactly a prime factor in my Plückel coordinates of the product of all my Plückel coordinates. So it's just, again, it's somehow, to me, it's really fascinating that the infrared divergences, again, handed to me from above, I know that infrared divergences are bad, that this is where the physics gets very, very strange. And they really correspond to understanding the behavior of the Feynman integrals at this very algebraic object, right? I have a polynomial, the prime factor of my coordinates, I'm just going to make something up, is going to look like something like a to the fifth bc minus de squared f squared, right? So I'm going to have what are my prime factors? It's going to be a bc minus de f. Those are my three prime factors. That's what I mean. So if I somehow my infrared divergences understand, actually I should just leave that there. Somehow my infrared divergences understand how to take this polynomial as formed by multiplying all of my Plugger coordinates together and then just looking at their prime factors. Again, like there is some deeper connection here that I just don't know how to find out more about. Okay, so let's talk more about these prime factors. Okay, we talked already about how positroids have boundaries, right? Like we had this 2x2 cell, it had three one-dimensional boundaries, and each of those one-dimensional boundaries have two zero-dimensional boundaries, and they really do form a nice little triangle and do the boundaries as they want. All of the divergences that we talked about before on the previous slide lie on boundaries. That's of my positroid cells. So maybe I should just write that down. So infrared which is, again, that's where the prime factors, the Plugger coordinates, that's how you start being able to see that. The interesting thing is not all boundaries correspond to infrared divergences. So there's a subset that are special, and then there's some of them that don't give rise to infrared divergences. And I would really love to understand, what's going on with those guys. Okay. The other thing that is also kind of just an open question. One of the things that I showed earlier is that when I'm asking the question fundamentally of what's going on when two particles collide, the way I understand that question is I expand it out in terms of more and more complicated diagrams. And the analogy here breaks down a little bit because I haven't talked about what loops are versus tree level diagrams, but ignoring all of that, there is an interesting question of, okay, so if I only had one of these helicity violating, one of these special propagators in my diagram, well, I can write down the matrix for that. And then now I want to add another. Well, that's just adding another row to my matrix. And now I add a third one, and I add another row to my matrix. Now, where things break down is that this here is in GR18. It's rank 1. This is in a completely different Grassmannian. This is rank 2. And here, this is in GR38. This is rank 3. So everything that I've been talking about with boundaries, I haven't been changing the ranks. I've just been changing Plugger coordinates. Here, I'm changing the Plugger coordinates and the ranks. So it's a little bit more complicated, but there is a mathematical structure that deals with this, just called a flag manifold. And if I was still math professing for a living, I would really love to spend a good deal of my time and some graduate students' time trying to figure out what the connection between flag manifolds and adding propagators are. Because that's not something I'm going to be able to do on evenings and weekends, but that's a really, it's a deep question, and understanding what's going on as we add more propagators is something that physicists just don't know. Like, they have an intuition for it. It's what we do when we do Feynman integrals, but yeah, there's just not a whole lot more now. Right, that was my last slide. So thank you for your time. I'm going to stop sharing. If you have any questions, please ask. Oh, I do see that there's a question in the chat.
Don't stop sharing yet. I do have
okay.
Sorry. So for the flag manifold now, are they just thinking this could be the flag manifold, or have they already found connections with the flag manifold?
No, this is my conjecture.
Oh, okay. I see.
Yes, this is my conjecture that that the way to understand adding more propagators is by looking at the flag manifolds here.
Okay. Okay. So I think the flag manifold structure could be explaining
Yes.
what are they called again? Propagators. Propagators.
Yes, the propagators. Yes.
Right, right. Could you explain a little bit more about the prime factors?
The what
Like
factors?
the prime factors. So
Oh, sure. Yeah.
yeah, I was a little bit confused about how to get the prime factors in.
Okay, so let me actually just do this. Let me do page actions. Maybe I can insert a page. Yep, there we go. Okay, and let me just start with a simpler example. Does that work?
Yeah.
Okay, so just I'm going to do 6. All right, that's not 6. Try again. Okay, 1, 2, 3, 4, 5, 6, and I'm just going to do something very simple like that. And here I will actually I will not be lazy, and I will label them all separately. So I can do A, B, 0, 0, C, D, and I can do 0, E, F, G, H. Those are my 8 variables.
Mm-hmm.
Okay, so now I can take a look at what all of my Fluker coordinates are here. Right, so my Fluker coordinates, so my first one is going to be AE. My second one is going to be BF. I'm sorry, let me keep going. AE.
Wait, sorry.
A,
For the second, when we're defining those, are we so the ones that support one end, that's the entries that should be non-zero. Is that correct? So the second line is connecting line 1, 2, and 3, 4.
this one here.
Right. So is the
Yeah.
second one that's connecting 1, 2, and 3, 4?
Yeah.
So why is the first entry
Oh,
0?
because I made a mistake. Thank you. So yes, you're right. This is E, F, G, H, 0, 0. Yes, thank you.
Thank you.
Yes. Well, you're following. That's good. No, seriously, thank you. I made a mistake. Okay, so what I have, my prime factors, so I have AF minus EB. That's the first one. Now I have AG, and now I have AH. And then the rest of them are going to be zero. And then I have EC, and I have ED. That's everything starting from 1. Now I have BG, and then I have BH, and then I have FC, and I have FD. Then I go to the next one, I get GC, so this becomes a 3, and this becomes a 3, and I have GD, so this becomes a 4. Where's my D? This becomes a 3. Let me just move this down a little bit. Right, and then I have H becomes a 3, C becomes a 4, and H becomes a 4, D becomes a 4. So my prime factors are A, F minus E, B, A, G, H, E, C, D, B, F.
Okay.
So when I look at the Feynman integral that's associated to this, what actually there's, right, I didn't go into this in detail, but the Feynman integral, there's some sort of a function up here, and then actually in the denominator is exactly, I'm just going to make a copy of that term. And so when I say understanding these infrared divergences corresponds to setting one of these guys to 0, I am literally evaluating this integral at a pole.
Right. Right. One of them becomes 0.
Yes.
I see. I see. Thank you. Thank you.
So again, it's just like completely physical laws somehow have this deeply geometric interpretation.
Very interesting. Okay. Does anyone have any questions? I posted a link to the PD hour form. And if you have any questions, please type in the chat, or you can just unmute and ask. And let's thank our speaker for the very interesting talk. I have really haven't thought about physics at all for many years. Thanks so much for bringing this up. And matroids as well. I've read about matroids when in graduate school, but I haven't thought about that for a few years.
Well, the nice thing here is that you don't have to think about the physics. You can just think about the geometry, right?
Right.
Like, I don't know.
Right.
That's why I love this stuff. Thank you so much.
Oh,
Feel
thank
free to
you.
reach out if you have questions.